Hi, hello and welcome to another session on digital signal processing. In today's session, we'll see the introduction about the IIR filters. So these are the two types of filters. One is the IIR filter, the second one is the FIR filter. So if you see the features of IIR filters, in IIR filters there is a feedback connection to get the desired filter implementation. Okay, so there is a feedback connection from the output back to the input. And also the impulse response, it is of infinite duration. That's why we call them as infinite impulse response filter. And other name for this is, they are also known as recursive filters. Okay, so in this recursive filters, the output depends upon the present input, past input as well as the past outputs. So these are some of the features of this infinite impulse response filters. Next, if we see the features of this FIR filters, in these FIR filters, there is no feedback connection from the output to the input, and their impulse response is of finite duration, and these are also known as non-recursive filters. So in this FIR filters, the output depends upon the present input and the past output. Okay, so these are finite impulse response filters. Next, if you see the examples of these analog and digital filters. So if you see this analog filters, we use the Laplace transforms to represent the analog filters, whereas the Z transforms are used for representing the digital filters. So this is the filter function in Laplace form. We write this as HA of S is equal to Y of S by X of S. So this is the filter function representation, summation k equal to 0 to m bk into s raised to k divided by summation k equal to 0 to n ak into s raised to k. So this HA of S, this A means the suffix, this suffix means that it is an analog filter. Okay, so this Laplace transform of HA of t, this HA of t is the filter function in the time domain. So when you apply the Laplace transform on this filter function in time domain, we get the filter function in Laplace domain, that is HA of S. So this is equal to integration minus infinity to plus infinity HA of t into e raised to minus st into dt. So for representing this analog filters, we use the constant coefficient differential equations. So this is the equation, summation k equal to 0 to n ak dk y of t by dt to the power of k. This is also equal to summation k equal to 0 to n bk d to the power of k x of t by dt to the power of k. So here x of t is the input of the filter and y of t is the output of the filter. Next, we will see one example of this analog low pass filter and a digital low pass filter. So if you see this diagram, this is an LC filter. It has two components, one is the inductance and the capacitance, which are connected in the form of an L. So this is an LC low pass filter. We apply the input V in and we get the output V naught. So if you see this diagram, here we are applying a noisy input, and if this noisy input is passed to this low pass filter, it gives a noise free output, because the high frequency components, they are the noise components. All of these high frequency noise components are removed by this low pass filter and we get a smooth output. So if you see the digital low pass filter, here this is an example y of n. So this digital filters, they are represented by using this difference equations, whereas analog filters, they are represented by using differential equations. So this is an example of a difference equation. Y of n is equal to 1 by 2 x of n plus x of n minus 1. So here x of n is the input and this x of n minus 1, this is the past input, that is the input delayed by one sample. So if you see this example, x of n plus x of n minus 1 whole multiplied with 1 by 2. So in this equation we have a summation term. So one adder is required, then we have a multiplication of 1 by 2. So we need a multiplier and also to generate x of n minus 1 from x of n. X of n minus 1 is the input delayed by one sample. So to generate x of n minus 1 from x of n, we can use a delay block. Okay, so this delay block generates this x of n minus 1 term. So all of these three components are required to realize this difference equation, which is in digital, which is the digital low pass filter. Okay, so here I have taken one example. You can see. So these are the inputs given to this digital low pass filter. So at minus 1 there is a magnitude of 5, at 0 we have 5.2, at 1 it is 5, at 2 it is 5.3, at 3 it is 5, and at 4 the magnitude is 4.9. Now if this input is passed through this digital low pass filter, so how to calculate the outputs? So this is based on this equation. You can see this above equation. We have taken 1 by 2 into x of n plus x of n minus 1. So here these are the values of n on the x-axis. You can start from 0, 1, 2, 3 and 4. So if you take n is equal to minus 1, if n is equal to minus 1, we need x of n minus 1 also. So x of minus 1 will be x of minus 2. But if you see in this diagram, there is no magnitude for minus 2. So I have started from n is equal to 0. So for n is equal to 0, substitute all of these in this equation. So y of 0 is equal to 1 by 2 x of 0 plus x of 0 minus 1. So 0 minus 1 is minus 1. So this is equal to 1 by 2 into, now see in the diagram, in this diagram we have x of 0. At 0 the sample value magnitude is 5.2, 1 by 2 into 5.2 plus x of minus 1. At x of minus 1 the magnitude is equal to 5. So 1 by 2, 5.2 plus 5, we get 5.1. Similarly for n equal to 1, y of 1 is equal to 1 by 2 x of 1 plus x of 0. So we get 5.1 here. Similarly for n is equal to 2, we get 5.15, and for n is equal to 3 we get 5.15, and for n is equal to 4 we get 4.95. So if you represent all of these samples in the form of a graph, so this is the output. So if you see the difference between the input and the output, there are more variations in the input, whereas if you see the output graph, there are comparatively less variations. So this is how a digital low pass filter works. Then we'll see the differences between analog filter and a digital filter. So if you see this analog filter can be implemented by using the active components or passive components, or the combination of both of these two. So active components are the diodes, transistors, FETs and all and so on, and passive components like resistors, capacitors, inductors. Whereas this digital filter, if you see the digital filter, this can be implemented by using the digital circuits such as adders, multipliers, delay elements, subtractors and so on. So the input given to this analog filter is in analog form, and the output is also in analog form. Whereas if you take this digital filter, both the input as well as the output, they are in digital form. An analog filter can be defined or can be represented by using the linear differential equations, whereas the digital filter can be represented by using a linear difference equation. And this analog filter, in this analog filter, the frequency response of the filter can be modified by changing the circuit components, whereas the frequency response of this digital filter, it can be modified by changing the filter coefficients. So this is all about the introduction of infinite impulse response filter, and something about this analog filter and digital filter. That's all, and thank you for watching.